Hello! In this video, we'll be looking at infinite sequences. An infinite sequence with this curly bracket notation with the nth term an inside is an infinite ordered list of numbers. Or you can also think of it as a function, not a continuous function, but one whose domain is the set of positive integers. So here in this notation, we have an, the nth term, inside the curly brackets. So that means it's an infinite sequence. And the values a1, a2, a3, a4, etc. are called the terms of the sequence. And an is the general nth term. In this example, list the first 5 terms of the sequence. So when n is 1, we just plug it into the rule for an. So 1 over 1 plus 1 is 2. When n is 2, we'll have 2 over 2 plus 1, which is 2/3. When n is 3, 3 over 3 plus 1, 3/4. When n is 4, it will be 4/5. And when n is 5, we have 5 over 6. In the next example, we have another form for an, negative 1 to the power n times n plus 1 in the numerator, divided by 3 to the power n. So we'll have one term for every n, starting at n is equal to 1. So we have minus 1 plus 1 is 2 over 3. So that's the first term when n is 1. When n is 2, the sign will be positive since we have minus 1 squared. And we have 3 over 3 to the power 2, which is 9. When n is 3, it will be negative again since we have minus 1 to the power 3. In the numerator, we'll have 3 plus 1, which is 4, over 3 to the 3, which is 27. When n is 4, it will be positive again since we have minus 1 to the 4. Then in the numerator, we have 5 over 3 to the 5, which is 81. And when n is 5, we have minus 6 over 243. And the sequence will continue, so I put ... Sequences are not continuous functions, and when you graph them, you will graph a bunch of isolated points. So for the sequence n over n plus 1, the graph is a bunch of dots. And we can see from the graph that for larger and larger n, the terms get closer and closer to 1. As n gets larger, an gets closer to 1, so we can define that the limit as n becomes large of n over n plus 1 will be equal to 1. In the next definition, we'll say that an infinite sequence converges to a limit if the limit as n becomes large of the nth term is equal to L. So if the limit is a real number, it converges. Otherwise, it diverges. And the value L will be called the limit of the sequence. There are a few ways to determine the convergence or divergence of sequences. The first way is just to compare f of n to a continuous function f of x. So if f of x has limit L, then the sequence f of n will have the same limit. So in the first example, we'll check the limit as x becomes large of 1 over 2x. Here we get 1 over 2 times infinity, which is infinity. So 1 over infinity will be 0. So 0 is a real number, so the sequence converges. Next we have the sequence root n, so we can compare that to root x. So take the limit as x becomes large of root x. That gives square root infinity, or infinity. So this is divergent. Next we'll compare ln of n plus 1 over n with the same function in x. So here we have ln of infinity over infinity. So here we can use L'Hopital's rule. For the inside of the logarithm, we'll just have 1 over 1. So here we get ln 1 is equal to 0, and the sequence converges. If you didn't use L'Hopital's rule, you could also have circled out the highest degree terms from the top and bottom. And since they have the same degree, we know it will be the ratio of the coefficients, which is also 1. Then ln 1 is equal to 0 would have given the same limit for the sequence. In the next example, again, we'll compare it to the function in x. So here I'm getting infinity over infinity, and we can circle out the highest x terms. We'll compare it to this limit. Here we can cancel x to the 10 in the top and bottom. So we get minus infinity, so the sequence diverges. So if you analyze the degrees, the degree of the top is larger than the degree of the bottom, so it will diverge. Next we have the sequence cosine of 2 over n. So we'll take the limit as x becomes large of cosine of 2 over x. So here we have cosine of 2 over infinity, which will be cosine 0, and cosine 0 is 1. So the sequence converges to 1. Next I have cosine of n over 2. So we'll compare that to the function cosine x over 2. And since cosine and sine keep oscillating, the limit does not exist. So the sequence is divergent. Next we have the sequence 1 plus 8 over n to the power n. So here when we take the limit as x becomes large, we have 1 plus 0, which is just 1, to the power infinity. So here we have an indeterminate power. So recall that the indeterminate powers were 1 to the infinity, 0 to the 0, and infinity to the 0. So I will call this limit y, and I will take logarithms of both sides. Now that it's a logarithm, we can bring the x in the front. Now when we plug in the limit, we have infinity times ln 1, and ln 1 is 0. We have the infinity times 0 case, which is an indeterminate product. So I'll bring x into the denominator, 1 over 1 over, or instead of x having power positive 1 in the numerator, I'll rewrite it in the denominator with power minus 1. You have ln 1, which is 0, over 1 over infinity, which is also 0. So now it's in the form 0 over 0, so we can apply L'Hopital's rule. The derivative of ln u will be 1 over u prime, and then the derivative of the denominator will be minus x to the minus 2. So the negative x to the minus 2 will cancel out in the top and bottom. So we have the limit as x becomes large of 8 over 1 plus 8 over x. Now when we plug in infinity, we'll have 8 over 1 plus 0. So ln y is equal to 8, so we can exponentiate to find y. Here we'll have e to the 8. So the sequence converges to e to the 8. The next technique is for a specific kind of sequence. It's when you have a ratio r raised to power n. So this is called a geometric sequence, and the geometric sequence is convergent when r is in between minus 1 and 1, and also equal to 1. The limit as n becomes large of r to the n is 0 if r is in between minus 1 and 1, or the absolute value of r is less than 1. So in that case, the sequence converges to 0. If r is just equal to 1, then every term is just 1, so the limit of the sequence is 1, and it's convergent. If the ratio is less than or equal to minus 1, then it will keep oscillating between negative and positive values, so the limit will not exist, and the sequence will be divergent. And finally, the sequence is also divergent for ratios greater than 1. In that case, the limit is unbounded, and the sequence is divergent. In this example, write the first 5 terms of the sequence. Does the sequence converge or diverge? Here we have a geometric sequence. It's the case where r is equal to 1, so we know that it converges to 1. Here we can write the first 5 terms, and 1 to any power is 1. So r is equal to 1, and the sequence converges to 1. Next we have the sequence minus 1 to the n. So when n is 1, it's minus 1. When n is 2, we have minus 1 squared, so it's 1. And here we see that the sequence keeps oscillating between the positive 1 and negative 1. So the limit does not exist and the sequence diverges. So for this geometric sequence, r is equal to minus 1. And the terms are always oscillating between minus 1 and 1. So the sequence is divergent. Next we have the sequence minus 2 to the n. So when n is 1, we have minus 2. When n is 2, we have positive 4. When n is 3, we have minus 8. When n is 4, we have 2 to the 4, which is 16. And when n is 5, we will have minus 2 to the 5, which is 32. So this is the case for the geometric sequence where r is less than or equal to minus 1. So in that case, it diverges. And we can see by writing the first few terms that the terms are getting larger and larger, and they're also oscillating between positive and negative. So you will never come to a limit, and the sequence diverges. Next we have the sequence 3 to the n. So 3 to the 1 is 3, then 3 squared is 9, 3 cubed is 27, 3 to the 4 is 81, and 3 to the 5 is 243. This is definitely divergent. You can see that the numbers are just getting larger and larger, so this geometric sequence diverges. Next we have the sequence 1/2 to power n. When n is 1, we have 1/2. When n is 2, we have 1 over 4. When n is 3, we have 1 over 2 cubed, which is 8. When n is 4, we have 1 over 16. And when n is 5, we have 1 over 32. Each time we multiply by half, the terms are getting smaller. So the limit of the sequence will be 0, and it will be convergent. Next we have the case minus 1/2 to power n. So this is very similar to the previous example, except that the terms will be oscillating between negative and positive. So in this case, the terms are still getting smaller, but they're also oscillating between positive and negative values. When we take the limit as n becomes large, it will converge to 0. So our geometric sequence, minus 1/2 in absolute value is less than 1. The sequence converges to 0. Next we have 2 to the power n plus 1 over 3 to the n. When we plug in n is equal to 1, we have 2 squared over 3, which is 4 over 3. When n is equal to 2, we'll have 2 cubed over 3 squared, which is 8 over 9. When n is equal to 3, we have 2 to the 4 over 3 cubed, so we'll have 16 over 27. When n is 4, we'll have 32 over 81. And when n is 5, we'll have 64 over 243. So here I'll just rewrite an, so it clearly looks like a geometric sequence. So on top you have 2 to the n plus 1. So that's 2 times 2 to the n over 3 to the n. Here we have 2 times 2/3 all to power n. So here you can see r is 2/3, and it's the case where the absolute value of r is less than 1. So we have a geometric sequence, and the sequence will converge to 0.